One of the central ideas of linear algebra and of higher mathematics is the concept of a vector space. So what's a vector space? Well, suppose I have a set of vectors v and a scalar field f. We say that the vectors form a vector space over f, or a f vector space, provided that all of the following conditions are met for all vectors u, v, w in our set of vectors, and all scalars a, b, c in our scalar field. First, we have to have closure under vector addition. When I take two vectors v and u, their sum is also going to be one of the vectors in our set. Next, we have to have closure under scalar multiplication. If I take some scalar c from our field f, then the scalar multiple c times my vector has to also be an element of my set of vectors. Third, we have to have commutativity of vector addition. v plus u has to be the same thing as u plus v. Next, vector addition must be associative. If I add three vectors, it shouldn't make a difference whether I add the last two first, or if I add the first two first, I should get the same result. But wait, there's more. We also want to make sure that we have a zero vector. So without committing to what it actually looks like, there should be some vector 0 that for any other vector that we choose, the vector v plus our 0 vector should just give us back the vector v. Tied very closely to that is the existence of an additive inverse. For any vector v in our set, there should be a vector that we'll designate as negative v, also in our set, for which the sum of the two vectors is 0. Next, while we have defined scalar multiplication by an element of f, we haven't committed ourselves to what happens when you multiply by the scalar 1, which is the multiplicative identity in our field. And if we are dealing with a vector space, we do want to require that the scalar multiple 1 times any vector should give you the vector itself. What about scalar multiplication? Well, I can't scalar multiply two vectors. That doesn't make any sense. But what I can do is I can multiply a vector by a scalar and another scalar, and so I would like to make a requirement for a vector space that we have what you can think about as associativity of scalar multiplication, that a times the vector bv is the same as ab times the vector v. And then I also want a distributive property of scalars over vectors. Now, this actually comes in two flavors. One possibility is I might have a scalar multiplied by the sum of two vectors. And I would like, if we're dealing with a vector space, for that to be the scalar times the first vector plus the scalar times the second vector. Now notice that what we've done is we've taken the thing on the left, which is our scalar, and distributed it among the things in the parentheses. And because we've taken the thing on the left and distributed it, this property is sometimes called left distributivity. And at this point you might ask yourself, could I have right distributivity? And the answer to that is a fairly carefully constructed yes. And in this particular case, what it means is that we're going to distribute a vector over the sum of two scalars. And so we have our second distributive property, which corresponds to what you might think about as right distributivity. If I have a sum of scalars multiplied by a vector, what I'm going to get is the sum of the scalar multiples of the vector. And so what we have are 10, count them, 10 properties that are required if we're going to be a vector space. And you may want to think about it this way. A vector space is sort of a very exclusive club that only certain types of things can join. To join club vector space, you have to meet all 10 requirements. So let's see if we can find some of these members of club vector space. Well, let's start out with a familiar set. How about the set of integers? And we do have to define what we mean by addition and scalar multiplication. So let's go ahead and just define them in our usual terms, where addition is our usual addition and scalar multiplication is our usual multiplication. So let's see if the set of integers has what it takes to become part of a real vector space. So remember that the real part of the definition refers to the field over which we're going to be conducting our operations. Alright, so the membership committee for Club Real Vector Space receives Z's application, and they go through the checklist. So first of all, we have to consider any three elements of our set. So let's take three integers m, n, and p, and we'll check out each item. So is the set of integers closed under addition? If I take two integers, do I in fact get another integer? And the answer to that is yes. Alright, now how about that closure under scalar multiplication? So for a real vector space, the scalars are going to be drawn from the set of real numbers. And the membership committee requires that the scalar multiple also be an element of the set. But if c is a real number but not an integer, then the scalar multiple c times an integer is not going to be an integer, which means that the integers fail the second requirement. Sorry, Charlie, you do not have what it takes to form a real vector space.